It's 3 a.m. You're fast asleep, but your AI agent isn't. You wake up to a notification that your API bill just spiked by $5,000 in only 4 hours. This isn't some hypothetical horror story. It's a very common reality for developers who treat agentic frameworks like magic black boxes. When you deploy an unconstrained agent, especially one built on early-stage frameworks without proper state management, it can fall into a recursive logic trap. It keeps calling the LLM, thinking it's refining its answer, while actually just burning through your API credits in an infinite loop. In the field, we call this the agentic infinite loop. It happens because the agent lacks a strict termination condition or fails to recognize it's repeating the same state. Before we talk about which framework is coolest, we need to talk about how to stop your code from bankrupting your company. This lecture is about that transition from playground demos to production-grade stability. But wait, is the problem the framework itself or how we architect the control flow? By the end of this session, you'll know exactly how to prevent this specific disaster. We've all seen the flashy demos on social media agents writing entire apps or managing complex schedules autonomously. But here's the cold, hard truth from the field. A cool demo is usually a production nightmare waiting to happen. In 2026, the industry has finally moved past the wow factor. We are now in the era of boring AI. Boring means predictable. Boring means reliable. Boring means when a user clicks a button, the agent doesn't hallucinate a new API endpoint or change its behavior randomly. My goal today is to shift your mindset from what can this agent do to how can I constrain this agent so it doesn't fail. To build production-ready agents, you need to understand that reliability is a feature, not an afterthought. We're moving away from black box autonomous agents toward observable, stateful graphs where every transition is logged and every failure is handled. If you want to build something that actually survives a Friday night deployment, you need to stop chasing autonomy and start chasing control. But how do we actually categorize the tools available to us in this shifting landscape? To navigate the 2026 landscape, you need to recognize the three heavy hitters: CrewAI, LangGraph, and Claude's native tool use. Think of these not just as libraries, but as three different philosophies of control. CrewAI is the manager. It's high-level, role-based, and great for quick orchestration, but it can be a nightmare to debug when the crew goes rogue. LangGraph is the architect. It treats agents as cyclic graphs, giving you granular control over state and transitions, which is essential for complex, long-running tasks. Then there's Claude tool use, which I call the minimalist. It's the raw power of the model directly interacting with your functions without the overhead of a heavy framework. Choosing between them isn't about which is better. It's about matching the framework's constraints to your project's risk profile. Most developers fail because they pick the framework with the most GitHub stars rather than the one that fits their state management needs. Now, let's look at how we even got to a point where we need such complex graphs to manage a simple LM call. The journey to agentic AI didn't happen overnight. It started around 2023 with linear prompting, simple input-output flows where the LLM was just a glorified text processor. Then we moved to chain of thought and basic RAG, where we started feeding external data into the context. By 2025, we reached basic agentic loops, where frameworks like AutoGPT promised full autonomy but delivered mostly instability and high costs. Now, in 2026, we've entered the stateful graph era. We've realized that for an agent to be useful in a professional setting, it needs a clear memory, a specific set of tools, and a strictly defined path of execution. We've shifted from asking the LLM to do everything to designing systems where the LLM is just one node in a larger, human-in-the-loop architectural graph. This evolution reflects a growing maturity in how we view AI not as a replacement for software logic, but as an enhancement to it. But wait, if these frameworks are all headed toward the same graph concept, why are their implementation patterns so radically different? In the next chapter, we'll dive under the hood to see the three different philosophies in action. In the production trenches, we often see developers get dazzled by how quickly they can spin up an agent team using CrewAI. Its philosophy is rooted in role-playing. You define a researcher, a writer, and a manager, much like you would organize a real-world department. It abstracts the complex LLM calls into high-level personas. On paper, this is brilliant for rapid prototyping. However, this heavy abstraction is a double-edged sword. When your production logs show a hallucination or a loop, you often find yourself fighting the framework's internal logic rather than the model itself. It feels like managing a black box where the agents decide how to talk to each other, which is great for a demo but can be a nightmare when you need 99.9% reliability. You start realizing that the ease of use comes of granular visibility. The crew handles the orchestration, but do you actually know what's happening at step 4 of a 10-step task? Often, the answer is no, and that is where the hidden technical debt begins to accumulate. But wait until you see how this abstraction actually handles complex task delegation in the real world. When we move into task delegation, CrewAI offers two primary modes: sequential and hierarchical. Sequential is straightforward: agent A finishes, then agent B starts. But the hierarchical process is where the manager agent comes in, using an LLM to decide which sub-agent should handle the next subtask. In a production environment, this is highly unpredictable. If the manager agent gets confused by a weird edge case in the input data, the entire pipeline collapses or, worse, enters an infinite loop of delegating without doing. I've seen teams spend weeks fine-tuning the manager's prompt just to get it to stop passing tasks back and forth. While it looks like a clean organizational chart, the underlying reality is a series of non-deterministic API calls that can vary wildly with every model update. You lose the deterministic flow that standard software engineering thrives on. If your business logic requires strict adherence to a specific path, this autonomous delegation might be your biggest enemy. This leads to a critical question. If we can't trust the manager agent to be consistent, how do we regain control of the flow without losing the agentic power? This is exactly where our next framework takes a completely different turn. If Crew AI is HR department, LangGraph is a state machine. It treats agentic workflows as a cyclic graph where state is a first-class citizen. This is a massive shift in philosophy. Instead of hoping a manager agent does the right thing, you explicitly define the nodes and the edges. The key power here is cycles and persistence. In traditional chains, once you move forward, you can't easily go back or pause. LangGraph allows the system to loop back to a previous state for correction, and most importantly, it can save the state to a database at any point. This enables human-in-the-loop workflows where the agent pauses, waits for a human to click approve in a dashboard, and then resumes exactly where it left off. In the real world, this is the difference between an AI that might work and an AI that is controllable enough for high-stakes enterprise tasks. It's built on top of LangChain, but it strips away the magics in favor of explicit control. You are basically writing a distributed system where the transitions are governed by LM logic or hard-coded rules. However, this control comes with a steep learning curve that many developers underestimate. But wait, what does this actually look like in the code when you're trying to debug a complex failure? Let's look at the code structure. In LangGraph, you define a type dict for your state, which acts as the single source of truth. Every node is just a function that takes the current state and returns an update. This looks and feels like standard backend development, which is why senior engineers often prefer it. You have total control over conditional edges, the logic that decides which node to visit next. If the LLM output doesn't meet your schema, you can programmatically force it back to a correction node without relying on the model to realize it made a mistake. This explicit flow mapping makes debugging significantly easier because you can trace exactly which edge was taken and why. You aren't just sending a prompt, you are managing a state transition. The downside, the boilerplate is real. You'll write significantly more code compared to Crew AI to achieve the same initial result. But in production, this boilerplate is what saves you during a 2am incident response because you can see the exact state of the graph at the moment of failure. You might think this is the ultimate solution, but is all this complexity always necessary? In some cases, the best framework is actually no framework at all. Now, let's talk about the native approach. Since 2024 and heading into 2026, models like Claude 3.5 Sonnet have become incredibly proficient at tool use, or function calling, directly via their API. Many developers are realizing they don't need a heavy orchestrator for 80% of agentic use cases. When you use Claude's native tool use, you are stripping away layers of framework overhead. This results in significantly lower latency and fewer framework-induced bugs. There's no complex state management to learn, no agent personas to fine-tune. You just provide a JSON schema of your tools and let the model output the call. This simplicity is a feature, not a bug. In production, every millisecond and every layer of abstraction counts. If your agent is just querying a DB and sending an email, why wrap it in a graph or a crew? You avoid the abstraction tax, the extra tokens and processing time frameworks add to manage their internal state. However, the catch is that you are now responsible for the orchestration logic yourself. You are writing the loop that handles the tool output and sends it back to the model. Is this trade-off worth the performance gain? Let's compare the overhead directly. When we compare native API calls to framework abstractions, the difference in surface area for failure is striking. In a native SDK call, you provide a clear JSON schema. If the model fails to follow it, you catch a standard validation error. In a framework, that error might be swallowed, retried, or transformed into a different agent state, making it harder to diagnose. The native approach forces you to be a better prompt engineer because you aren't relying on the framework's hidden prompts to make the agent work. You see every token. For a production-grade system where you need to scale to millions of requests, the framework overhead can add up to thousands of dollars in extra token costs and seconds of latency. However, as soon as your workflow requires complex branching or long-term memory, the native approach starts to feel like you're reinventing the wheel. You'll end up writing your own mini version of LangGraph. So the real skill isn't knowing how to use a framework. It's knowing when to stop using one. Now that we've seen the 3 philosophies, how do we actually decide which one to pick for a real project? In the next chapter, I'll give you my 5-axis production matrix to make that decision foolproof. In a production environment, the biggest nightmare isn't the code failing. It's not knowing why it failed. When an agent enters an infinite loop or hallucinates a tool argument, you need deep observability. LangGraph shines here because it was built from the ground up to integrate with Langsmith. You can see every state transition, every token, and every node input-output in a clean trace. Crew AI has made strides, but often feels like a black box where the internal reasoning is hidden behind layers of abstraction, making it difficult to pinpoint if a failure was due to the prompt, the tool, or the agent's logic. If you are deploying for a client where every millisecond and every penny counts, you cannot afford to guess. You need a framework that exposes its guts through standard tracing protocols or native integrations. But observability is just the first axis. Knowing what happened is one thing, ensuring it doesn't happen again is another. This brings us to the core issue of predictability. Can we actually control these agents? But wait, does observability automatically lead to a stable system? Not quite, because even a perfectly observed system can be inherently unpredictable. When we talk about determinism in agentic AI, we are essentially fighting the probabilistic nature of the LLI. In crew AI, you delegate tasks to agents and trust they will follow the process. This is great for creative workflows, but in a production banking or medical app, trust is a liability. LangGraph treats the agent as a state machine. This means you can explicitly define valid transitions. If an agent is in state A, it can only go to state B or C based on logic you write. This level of determinism is what separates a toy from a tool. Claude's native tool use takes this even further by removing the framework abstraction entirely, giving you direct control over the loop. However, the more control you take, the more boilerplate you write. You have to decide, do you want the framework to figure it out, or do you want to define the guardrails yourself? In practice, most developers start with the easy path and regret it when the agent starts hallucinating new tools that don't exist. But what happens when the agent actually encounters a real error, like a 404 from an API? In the real world, APIs fail, networks lag, and LLMs give malformed JSON. How your framework handles these bad days defines your production readiness. Crew AI relies heavily on internal retree logic buried within its task execution. It tries to be smart, but sometimes it just repeats the same mistake until the max RPM is hit. LangGraph, conversely, allows you to model error recovery as a specific node in your graphs. You can create an error handling node that inspects the exception and decides whether to retry, ask the user for help, or roll back the state. This is human-in-the-loop capability by design. If the LM generates a bad SQL query, LangGraph can catch the database error and feed it back to the agent for a correction cycle. This structured retry mechanism is vital for building resilient systems that don't just crash when things get messy. But this reliability comes with a hidden tax, specifically a token tax. Does the framework's internal management consume more than it provides? Let's look at the actual costs involved in these complex recovery loops. Let's talk about the token tax. Every framework adds its own system prompt instructions to manage the agent persona. Crew AI is notorious for adding large, descriptive prompts to ensure agents stay in character. This might consume 500 to 1,000 tokens per call before you even get to your actual prompt. Over thousands of runs, this becomes a significant overhead. LangGraph is more modular. While LangChain has its own overhead, the graph overhead itself is minimal, focusing more on state management than personality prompts. Claude's native tool use is the cleanest, adding almost zero overhead outside of the tool definitions you provide. In my experience, developers often ignore this until the first monthly bill arrives. You need to weigh the ease of use against the framework overhead. A more automated framework might save you 3 days of development, but cost you $10,000 extra in annual API fees. Is the abstraction worth the premium? Now that we've analyzed the matrix, let's look at a real-world scenario to see these trade-offs in action through code. Let's build a typical business automation. We receive an email, parse it, query a database for customer history, and then notify the team on Slack. In Crew AI, this is defined by agents and tasks. You define a customer success agent and a database researcher. The framework handles the handover automatically. Notice how clean the code looks. It's almost like writing a project requirements document. You define the tools and the agents, and the process orchestrates them. This is excellent for rapid prototyping or simple sequential tasks. However, if you need the database researcher to go back to the email agent because the data was missing, the logic becomes fuzzy. It's built on a manager-employee mental model. While this abstraction is powerful for speed, it can lead to unexpected behaviors when the employees start talking too much. Does this ease of use mask a lack of control? Let's see how the same logic looks when we need more granular precision in LangGraph. Now let's look at the LangGraph version of the same workflow. It's more verbose, but every step is explicit. We define a state dictionary to hold our email content and database results. Each function represents a node in our graph. The rotor decides where to go next. This might look like more work, but it gives you God mode over your agent. If you want to add a rule that says only notify Slack if the customer's lifetime value is over 1,000, it's a simple if statement in a node. In Crew AI, you'd have to prompt the agent to be careful about the value. In LangGraphs, you just code the logic. This is why for production-grade, business-critical logic, many senior developers migrate here. You aren't just crossing your fingers and hoping the LLM follows instructions. You are enforcing a workflow while letting the LLM handle the unstructured data within the nodes. But is even this too much? What if you want the absolute bare minimum and maximum performance? Finally, we have the Claude native tool use approach. Here, there is no magic. You are responsible for the loop. You send a message to Claude. It tells you which tool to call. You call the tool in your own Python code, and you send the result back. This is the cleanest architecture because it has no dependencies on third-party agent libraries. If Anthropic updates Claude 3.5 to 3.7, you just update your API calls. For high-throughput applications where latency is king, this is often the winning choice. You avoid the framework bloat and have total control over the prompt and the context window. The downside, you have to write your own state management, your own retrieval logic, and your own logging. It's the build vs buy dilemma at a framework level. Most teams find that while frameworks are great for getting started, the most robust production systems often end up looking a lot more like this direct implementation. We've seen the matrix in the code, but where do these frameworks actually break in the wild? In the next chapter, we'll dive into the real battle stories, the exact moments where these frameworks failed in production. Everyone loves crew AI for their first POC because it feels like magic. You define an agent, a task, and a crew, and it just works. But here is the reality check from the field. The abstraction wall is real. When you need to intercept a specific tool call to inject custom logic or modify the internal prompt template that crew AI uses for its manager agent, you hit a brick wall. In one production case, we needed to modify how agents handled a specific JSON schema error, but because the logic was buried deep in the framework's high-level API, we had to resort to messy monkey patching. This is the classic trade-off where ease of use at the start becomes a maintenance debt later. If your business logic requires granular control over every token and transition, that high-level abstraction becomes a cage rather than a tool. You will find yourself fighting the framework more than building the feature. But wait, if high-level is too restrictive, is going low-level always the answer? Let's see what happens when you try to map every single state manually. So you decide to move to LangGraph for total control. You want to see every node, every edge, and every state transition. Then the nightmare begins, the circular reference bug. In a complex graph with 15 nodes, one senior developer spent 3 straight days debugging why an agent was stuck in an infinite loop between 2 reasoning nodes. Because LangGraph forces you to define the state schema and every transition explicitly, a tiny logical error in your should continue function can lead to a recursive disaster that drains your API credits before you can say stop. It's a war story that happens more often than you'd think. The cognitive load of managing a massive directed acyclic graph, DAG, manually is the price you pay for that control. You move from being an AI developer to being a graph orchestrator, and the boilerplate code can quickly dwarf your actual business logic. Does this mean more control is just a different kind of trap? Let's look at the third path, going native with a specific provider. Then there is the native Claude tool use route. It is incredibly fast and reliable because it skips the framework overhead entirely. You use Anthropic's SDK, you define your tools in their specific JSON format, and the responses are crisp. But here is the trap, vendor lock-in. By building your entire agent logic around Claude's specific tool calling cycle and prompt structure, you are effectively tethering your product to one provider. If a better model like Llama 4 or a cheaper GPT drops tomorrow, migrating your agent will require a complete rewrite of your tool handling layer. We saw this when teams built heavily on top of early OpenAI function calling only to find their logic didn't translate to other models. Building framework-agnostic layers might seem slower now, but it's your insurance policy against a shifting AI market. So we've seen how frameworks fail at abstraction and complexity, but there's a silent killer that eats your budget regardless of which framework you choose. I'm talking about context window bloat. Most developers treat agent memory like a simple list, just appending every message to the context window. In a long-running production agent, think a customer support bot, this is a recipe for disaster. By the 20th interaction, your context window is bloated with irrelevant small talk, and the model starts losing the needle in the haystack, your actual system instructions. This leads to context drift where the agent forgets its original purpose or starts hallucinating based on outdated information. In the field, we solve this with rolling summarization or vector-based memory retrieval, but many frameworks don't handle this out of the box in a way that's cost-efficient. If you don't explicitly manage what stays and what goes, your API costs will scale exponentially while your agent's intelligence scales downward. You need a strategy to prune the fat from your context. But how do you keep the agent state alive if the server crashes in the middle of a complex thought process? This leads us to a critical production feature. In production, persistence isn't just about saving logs, it's about checkpointing. Imagine an agent performing a 10-step data migration. At step 8, the network blips or your container restarts. Without a robust checkpointer, you start from step 1, doubling your cost and potentially creating duplicate data. This is where LangGraph shines compared to simpler frameworks. Its checkpointer saves the state of the graphs at every single node. If it fails, you can resume from the exact point of failure. I've seen this save hours of manual cleanup in large-scale automation pipelines. When evaluating a framework for 2026, don't just look at how it starts, look at how it recovers. A framework that cannot persist its brain state to a database is just a toy for demos, not a tool for the enterprise. But even with perfect recovery, there is one thing an agent should never do alone. Let's talk about the human-in-the-loop requirement. The most dangerous agent is one that is 100% autonomous with 0% to supervision. In high-stakes environments like financial reporting or production deployments, you must implement human-in-the-loop, ITL. This isn't just about asking for permission. It's about the framework's ability to pause and wait for external input without losing its execution context. LangGraph's interrupt feature is a gold standard here. It allows the agent to reach a sensitive node, save its state, and wait for a human to click a dashboard before continuing. I've seen projects fail because they assumed the AI was smart enough to make 5,000 decisions solo, only to have a hallucination cause a massive financial error. Production-grade agents in 2026 treat humans as just another special node in the graph. Now that we've covered the battle scars and the failures, you're probably asking, which one do I actually pick? In the final chapter, I'll give you the exact decision tree I use to choose the right framework for every project. In the field, the most common mistake isn't choosing the wrong framework, but choosing one that doesn't fit your specific failure tolerance. If your project requires absolute control over the state, meaning you need to know exactly why the agent moved from point A to point B, then LangGraph is your only serious choice in 2026. Its cyclic graph approach treats state as a first-class citizen. However, if you are building a collaborative multi-agent system where emergent behavior is a feature, not a bug, CrewAI's role-playing architecture will get you to a prototype 50% faster. For simple, linear tasks where the LLM just needs to call a function, skip the heavy frameworks entirely and use Claude's native tool, use API. The decision tree isn't about which library is better, it's about which one gives you the right level of controllability versus autonomy for your specific business logic. But what happens when your project demands both rigid control and creative problem solving? That leads us to the hybrid architectures currently dominating the enterprise landscape. Experienced leads know that for production-grade AI, a one-size-fits-all approach is a recipe for disaster. We are seeing a massive shift toward hybrid models. Imagine an enterprise system where LangGraph acts as the director handling the rigid workflow and compliance checks, while specific nodes within that graph trigger CrewAI sprints for creative research or Claude's direct tool calling for high-speed data fetching. This layered approach prevents the agentic loop from burning through your budget while ensuring you aren't stuck with a brittle, hard-coded script. You must decouple your orchestration layer from your execution layer. If your framework choice makes it impossible to switch models or modify the state externally, you've built a legacy system before you've even launched. This sounds great on paper, but the real test comes when you actually hit the deploy button. Let's look at the checklist that separates the juniors from the seniors in 2026 production environments. Before you even think about production, you need to run your agent through a gauntlet of what-ifs. In the field, we see agents fail not because of the LLM, but because of infrastructure gaps. Do you have a maximum loop limit? Without it, a hallucination can cost you thousands in API credits in minutes. Are you logging every state transition or just the final output? If you can't replay a failed session, you can't debug it. We also check for timeout handling. If a custom tool takes 30 seconds to respond, does your framework hang or fail gracefully? Most importantly, you must have a circuit breaker for repeated failures. If the agent fails the same task 3 times, it must stop and alert a human, not try a 4th time with a different prompt. This checklist is your safety net in an era where software can literally think itself into a corner. Is your architecture ready to survive a 404 or error from an external API? Let's refine these principles to ensure your work survives the next framework update. The framework war will continue long after 2026. Today it's CrewAI or LangGraph. Tomorrow it will be something else entirely. The secret to longevity in this field is to build agent-agnostic logic. Keep your prompts in separate managed files, treat your tools as standalone microservices, and keep your core business logic outside of the framework's proprietary classes. If you can't swap LangGraph for a custom Python script in a weekend, you've overcoupled. Focus on observability, because in agentic systems, the we is more important than the what. By following the principles of modularity and strict state management, you ensure that your system remains relevant regardless of which AI model or library takes the lead. This is how you build for the future while delivering value today. Now that we have our decision tree and our deployment safety net, let's wrap up this journey with a final set of action items to get your production system live. Ready to move to the final chapter and see how to put all of this into immediate practice. Look, the industry hype around agents is deafening, but production reality is brutal. We've compared CrewAI, LangGraph, and direct Claude tool use. CrewAI is your fast track for collaborative roleplay, but its heavy abstraction can feel like a black box when things break at 2 a.m. in a production environment. LangGraph gives you the control you actually need for complex state machines and cyclic flows, though you'll pay for it in steeper development time. Then there's the minimalist approach, direct tool use with Claude, which remains the most reliable and low latency choice for single-turn utility. The golden rule I've seen in the field is simple. Choose the framework that requires the least amount of magic to explain your logic. If you can't draw the state transition on a whiteboard without using framework-specific jargon, you're probably over-engineering. Are you ready to see how these theories actually hold up when the API starts throwing 500 errors or your tokens start spiraling? The path forward isn't about reading more docs. It's about breaking things. Start by building a proof of concept using the direct tool use API first. It's the cleanest way to understand how your LLM interacts with external functions without the overhead of an agentic layer. Once you hit the wall where you need persistent memory or complex cycles, that's your signal to migrate to LangGraph or CrewAI. In 2026, the most successful AI engineers aren't agent experts, they are reliability experts. They focus on observability, implementing tools like Langsmith or custom traces from day one to catch non-deterministic failures before they hit the end user. Don't build a swarm if a simple function call will do. Take the decision tree we discussed and apply it to a single, high-value internal process. This is where the real learning begins, far away from the sanitized examples of a tutorial. You've now got the map. It's time to go into the trenches. This concludes our deep dive into the agentic framework trap. Now go build something that lasts.